Yogi, can we start?
Uh,
Yogi?
yes, sir. Sir.
Yeah. Could you please confirm whether Professor Kavitha joined in this session? Professor Kavitha, ma'am, are you there?
Yes, sir, I'm there. Am I audible?
Yeah, ma'am. Yeah, ma'am. If you start the session, ma'am, I will give you just a brief
Yes, sir.
about it. Yeah. Yeah. Good afternoon, everyone. It is with a great pleasure that I extend a warm welcome to all of you to this 6 days online faculty development program on emerging trends in civil engineering for disaster management. As you are aware, we are at the last day of this faculty development program. Actually, this session is supposed to start at 2 p.m. Based on the demand of participants, we reschedule this program from 3 to 8, 8:30. Here we may have three sessions. Session 11 will be taken by Professor B. Kavitha from 3 to 4:30 p.m. After taking a break from 4:30 to 5, as many faculty members may leave the colleges or that duration, we will restart the session 12 at 5 p.m. And after session 12, we may have an immediate session by uh, expert from Bentley. After session 13, we may have one online session followed by valedictory. Now, coming to our program, coming to our today's speaker, today we are pleased to have Professor B. Kavitha as expert of this session 11. Dr. B. Kavitha is an assistant professor in the engineering structure division of the civil engineering department at NIT Warangal, Telangana, India. She completed her PhD in structural engineering from IIT Madras. She also holds an ME in structural engineering from Kamaraguru College of Technology, Tamil Nadu, where she earned a gold medal for her excellent performance, and a BA in civil engineering from Sri Krishna College of Technology, Tamil Nadu. Her research focuses on engineering seismology, earthquake data analysis, ground motion simulation, probabilistic seismic hazard assessment, and earthquake forecasting. Dr. Kavitha has worked on creating probabilistic seismic hazard maps for different regions of India under a project funded by MHRD Startup Research Grant. Before joining NIT Warangal in 2018, she worked as an assistant professor at NIT Tiruchirappalli. Her work is helping to improve the understanding and management of earthquake risk in India. We are very happy to have you here, ma'am. We are privileged to hear uh, the deep insights of earthquake design of reinforced concrete structures. Thank you very much for accepting our invitation. And over to you, ma'am. We are eager to hear from you.
Thank you, sir. Thanks for your nice introduction. Okay, we will start demonstration now.
Yogi, could you please allow ma'am to share her screen?
Yeah. Madam, you can directly share the screen.
Okay.
Ma'am, if slideshow is not working, hello.
Yes, sir, you are audible, sir.
If slides,
Yes, sir.
Madam, have you shared the screen? Madam?
You are not audible, sir. Your voice is not clear.
Madam, have you shared the screen, madam?
I have shared the screen, but I couldn't make it full window.
Oh. Okay.
Maybe I will rejoin again, sir. 1 minute.
Okay, madam.
ma'am, RS, could you please convert it to PDF? Actually, here in this mode, slides may not move, I think. Could you please check whether the slides are moving or not, ma'am? Yeah, moving, it's moving, ma'am. Madam, a small suggestion from my side. If that slideshow is not working, there is another button behind that one, reading tab, reading view tab. It also works. Second one, ma'am. Yeah. Could you please move slides, ma'am? At bottom, you have option, ma'am. Yeah, it's working well, ma'am. It's working well.
Okay, can you see the slides now? Sir, can you see the
Yes,
slides
madam.
now?
Yes, madam.
It is moving?
It's not moving, ma'am.
Not moving.
Yeah. It might be great in a reading view, ma'am.
Yeah, it's reading view.
Yeah.
Just one second. Sir, am I audible?
Yes, madam. Yes, madam.
The thing is, I can able to change the slides, but by the same time, I couldn't see you people react. So what I will do is continue my slides. Okay.
Okay.
In between, I will stop and come back and ask if you have any questions.
Okay, madam. Okay, madam.
Okay.
Madam,
Thanks.
or else you can convert it to PDF and scroll down. That's also good.
Okay. That option is there. Okay. Let me try this.
Okay.
Hope I'm audible.
Yes, madam.
Okay. So we will start today's session. Today we are going to discuss about earthquake resistant design of structural elements. It may be a building, it may be bridges, or it may be a nuclear reactor. So whatever may be the case, how to design our structures safely against earthquake. That is our motto. For this, in our today's lecture, we are going to cover few aspects. First, we will see what is earthquake, how it is dangerous to our structures. Then we will move on to earthquake resistant design principles. Then finally, we will try to cover some of the applications or some of the techniques available in modern world. Today, what are the new techniques arrived and how those things are safeguarding our structures that we are going to cover at the last. So let us start. So these are the contents in our lecture. First, we will see why the earthquakes got sudden popularity among all other natural disasters. So that's the first thing we will going to discuss today. So why we are bothered about earthquakes is our structures. It may be a building or it may be a bridge, whatever may be the case. We are having a natural frequency of those structures which are more or less equal to our earthquake frequency, earthquake wave frequency. You know, whenever an earthquake comes, it is going to reach the sector in the form of simulation or seismic waves. These seismic waves are usually having a frequencies which is varying 0 to 50 Hz. Similarly, our structures, civil engineering structures, buildings or bridges are also having frequency more or less 0.1 Hz to 10 Hz. So one basic formula one you can easily remember, whenever you want to calculate the frequency of any building, you just by heart this formula 1 by 0.1 times number of stories. That is nothing but natural frequency of a building. What is natural frequency? If you start vibrating a building, it will start vibrating with your frequency in which you are start vibrating. But after some time, it is going to adapt its own natural frequency and it will start vibrating in that frequency. That is called as natural frequency. So whenever this natural frequency of the building and earthquake phase are getting resonance. So you heard about resonance, right? Resonance means whenever the same frequency is getting matched, there is a possibility that amplitudes will increase tremendously. So that we should avoid. That's why civil engineers are so much bothered about earthquakes and the seismic waves or seismic resistance got this much of importance nowadays. One more reason for this one is urbanization, or we can call that industrialization. So because of the population growth and other things, if you see in not only in India, world level, people are moving towards cities and where the population of cities are increasing tremendously. For example, this figure you can see in 2000, more than 140 super cities. Super cities means where we can expect more than 2 million population is there all around the world. You can imagine if this is the case in 2000, what will happen in 2050. So more than half of the populations are going to live only in urban cities. So one small event, if it is happening in this urban area also, going to bring a lot of loss to even economic loss and human loss also. So that's why because of the resonance property of our seismic waves and buildings and this urbanization, we are going to deal with this earthquake resistance with so much of care and importance. So that's a need for the subject first. Once we know the need of the subject, we will move on to what is earthquake, why it is happening, where it is happening, and how to describe an event and like that. Some basic things. If you know about these basic things only, you can able to design your structures safeguarding from this kind of vibrations. So many of you know what is earthquake. Earthquake is nothing but a sudden movement of our ground. Why this is happening? This is because of a seismic energy release which is got stored within our crust. Okay, where Earth is having a top layer that is called a crust. That crust is having this kind of elastic energy stored within the rocks. If it is suddenly releases, it is going to bring some vibration that we know. So from this earthquakes, we are going to see some basic terms involved. That is called as what is magnitude, intensity, and other things. Once we know about these things, we will move on to next terms. For example, why this earthquake is happening means if you see the world level, there are around 52 tectonic plates are there. Tectonic plates is, you can imagine that we know at the crust, that is the top layer, then mantle is there, inside we are having core. So whenever we are having this kind of differences in our earth, the temperature differences, it is going to bring some mantle convection. That mantle convection is the reason for earthquakes to happen. So because of this mantle convection, the topmost layer of the earth, that is, which is having so many small plates, as I told, there are 52 number of plates. These are going to be in movement always. These plates are going to struck between each other, are hit between each other, then we can expect events. So you can see this figure, it may make more clear to you. The temperature difference between mantle and crust is, this is 5000 degrees C, that is 12,000. So you can see because of the difference. So whenever you are heating your water in the plate, you can observe that the topmost layer is trying to go to down. The down layer will come to top. So like this, it is going to get rotated. Because of the rotation, so the topmost layer is going to be getting movement always. It may go away from each other. Sometimes it may come towards each other. So based on the movement, we are going to expect. See, these are the tectonic plates what we are discussing about. There are 52 number of plates, major plates also there, some minor plates also there. You can clearly see the differences in the size of the plate. This red color and yellow color what you are seeing is nothing but the earthquake epicenters. So you can obviously say that only along the borders of the tectonic plates, you are going to have more number of events. When you see the middle of the plate, you will be having events, but you are having very less number of events. So because of these movements, okay, we are going to have three types of boundaries or three types of faults. That is, if it is moving away from each other, I can call that as spreading. If it is going to come closer to each other, I can call that as collision. If these two are going to move just parallel to one another, one may go in the left, another go maybe in the right, without hitting each other, a smooth transition, then I can call that as parallel force. So spreading boundary is there, collision boundary is there, or parallel boundary is there. By these three type of movements, we are going to get three different types of earthquake waves or three different types of movements of tectonic plates. From this, you can get strike slip fault, thrust fault, or normal fault. Normal is nothing but your reference or left hand side will be stable. Your right tectonic plate will go down. If it is happening in the reverse order, your reference plate is staying, or left hand side is staying stable, your right portion is going towards the top, then you can call that as thrust. Okay. So one more case is without any disturbance, your left hand side tectonic plate is moving towards you, your right hand side is moving away from you. Okay, that is called as strike slip. So these are the three different types of faults. So what does fault may come as a question? Fault is nothing but a predefined or pre-existing crack in your tectonic plate. Tectonic plates are having boundaries, that is different. Inside the plates also, you may have this kind of faults. Faults is nothing but cracks. So tectonic plate boundaries will experience this kind of movements. So inside plates also, you will be having this kind of movements that is called intraplate events. So what that we will see later. Okay. So this figure will make so many other things also more clear. If you see our India, so you can see the Indian political boundaries and other things. You can see that only in the top Himalayan portion and in our Andaman region or Northeast region, you are having more number of events. That more number of events indicating that that is the plate boundary of our India, tectonic plate boundary of our India, where you can see the more number of events. When you see the other parts of India, maybe our South India or the Middle India, there and all you are having very less number of events, but still you are having those lines. That lines are indicating faults. These faults are responsible for these events, which very less number of events, although it is having very less magnitude. But in the boundaries where you can see the more number of events, these events are responsible for the tectonic movements that is hitting the another plate in that particular area. So you are getting more events, and also the events are having more depth as well as more magnitude. So this is the difference between interplate and intraplate of earthquake. So interplate, nothing but one plate to another plate because of hitting or movement or those. Intraplates is because of the faults. Faults is nothing but pre-existing cracks. So these are the two types of earthquakes. So how to describe an earthquake? For example, one earthquake happened. How to say that an earthquake is happened? Where it happened? How to define the place? So for that, people are usually using latitude, longitude, location. So you know what is location. You will define its x-axis and y-axis. In addition to that one, we will say the time of the event. When it happened, where it happened. These two are the important things, how we are going to describe an event. Then we will see what are the types of seismic waves. Seismic waves, whenever an earthquake happens, we are going to divide that earthquake wave into two different types. One is surface wave, another one is body wave. Okay, the difference between the surface wave and body wave is in which medium it is going to travel. So surface waves are usually travel along the crust. Okay. When it comes to body wave, it usually tries to go deeper and deeper through mantle, and again it will come back to crust. That's a basic difference. So why I want to study this medium of earthquake waves or the type of earthquake waves means this is going to tell you what are the different types of movements your structure is going to experience when an earthquake comes. For example, you may design your structures only for horizontal movement. You may imagine, because of event, I'm going to get only a horizontal movement. So I will design my structures to safeguard from only horizontal. But the thing is not true. Whenever an earthquake comes, that particular earthquake point, or we can call that as epicenter, from that epicenter, a huge seismic energy is going to get released. That seismic energy in the form of seismic waves, it is going to travel from that particular location to your own building, which is going to travel to different mediums. So it is going to bring so many other frequencies and so many different types of movements to your structure. So first we will understand these things. These are very basics, but still this is very important for you to know what are the things I have to provide to my structures to safeguard against earthquakes. So first thing is surface wave. You can see the figure. In this you can see P wave, S wave, Rayleigh wave and love wave. How these things are going to move. Okay, first we will say body wave, that is P wave. P wave is the primary wave, that is the fastest wave. Okay, it can go up to 1 to 14 kilometers per second. Okay, per second it can move up to 14 kilometers. Okay, you can imagine how it is, how fast it is. It is going to move in the form of expansions and compressions. Can you imagine from our left hand side, it is going to compress the particles, soil particles, then it will elongate the soil particles, then it will compress the soil particles, then it will elongate. Like this is going to move. So if your building is located on that particular soil, your foundation will experience some kind of crushing from both the directions. Then it will experience some pulling from both the directions. Can you imagine? So that kind of wave movements it is going to follow. Which one? P wave. Another type of wave is S wave. S wave we used to call as secondary wave. It can go up to 7 kilometers per second. So this one is going to follow a wavy pattern, up and down, wave pattern. So if your building is going to stay on this particular soil, you can imagine that particular foundation is going to experience an up and down movement, that to a wavy pattern. Okay. Then another type of waves is surface waves. Surface waves, as I said, it is going to travel only along the crust, topmost layer. So there we are having two different types. One is love waves, another one is Rayleigh wave. Rayleigh waves, it will travel in an elliptical path. Okay, one particular soil particle it's observed, it is going to get down and it is going to follow a circular path. Again, one more circular path, like this it is going to move. So just imagine if your foundation, it may be whatever may be the type of foundation you have selected, if it is lying in this particular soil and that soil is going to move in a circular pattern, so what kind of things you have to take care when you are designing that particular foundation? So next type of wave is love waves. It is going to follow a zigzag pattern. So whenever this seismic wave is passing through that soil, that particular soil particles are going to experience a zigzag particle movement. So why we are studying or why we are bothering about these things is, this seismic waves are the combination of all these movements. So whenever a seismic wave is going to come and hit your structure is going to experience all these type of movements underneath. All these types. At that time, these things may superimpose or overlap also. In addition to that one, when it is experiencing the first wave, sometimes another wave also may come and overlap on this one. So when you know some clarity, when you have some clarity about the seismic waves, then only your design will be proper against the future events. That's why it's important to know the wave patterns, its frequencies and amplitudes and types, so that you can easily design your structures to withstand these kind of movements. That's why this is also covered in this particular lecture. So next. Okay, this is what I have explained. What is compressional wave, what is shear wave, what is its amplitude, wavelength, frequencies, and other things. These things are taken care in our IS code. So if you follow our IS 1893, it will cover all these aspects. Okay, so what are the sources of this seismic waves other than earthquakes? Okay, seismic waves are responsible for earthquakes, are responsible from earthquakes. Whereas other types of elastic waves also there. It may be from volcanic eruptions, it may be from explosions, and some other human-made waves also there. So we will define some terminologies before moving on to our subject. First thing is epicenter. Epicenter is the projection of our focus. Okay? Focus means that is the place where the seismic energy is getting released, or else that is the point, okay? That is the place where earthquake started or originated. It may be below some 40 kilometers or 50 kilometers from your topmost soil layer. So there the earthquake happened means I have to call that place as focus or hypocenter. If I project that line vertically to the topmost layer, I will call that place as epicenter. Your building may be located away from that one. For example, earthquake has happened in some other place near to Delhi, but our building is situated in Madhya Pradesh. Then I have to call epicenter as Delhi. My building in Madhya Pradesh has to be called as site that observer. The location from my Madhya Pradesh building to Delhi is called as epicentral distance. So usually when you are defining the structures, the hypocentral distance from your origin to your building distance is important. So all your calculations you are going to use only this value. Okay, this value is called as hypocentral distance. Why this value is important means because this is the way the wave is propagated. This is the path the wave is followed. So through which all those medium properties or the elastic properties are disturbed or changed. So I am going to consider this hypocentral distance for my calculation. So what is magnitude is right at that one. So intensity is how you are feeling them. Focus and epicenter is clear, so that we can move on to okay. This I don't feel necessary for our subject. We'll go on this intensity scales also you would have heard about, and magnitude also. Magnitude scales also you must be first. So difference between these two, one is qualitative, another one is quantitative. Qualitative means, take for example, an earthquake, how it is going to disturb myself. For example, I may felt only the vibration, or sometimes I may my building may get disturbed. Sometimes my building may get collapsed. Also. So that difference, how it is going to affect me, is called that intensity. But magnitude is that is related to the seismic energy release. So how much energy is released in that particular position? Maybe it may be 30 kilometers or 40 kilometers below that topmost soil layer. So that quantity is called as magnitude. For example, if it is happening in the desert of magnitude 9, if it is not going to be bothered or it is not going to be felt by anyone, then the intensity may not be there. It may say that intensity 1 or 2. But the same thing happened in a city, that intensity may be very less, but the magnitude may be very less. The intensity we felt may be very. So that small relationship between the intensity and magnitude is based upon the position where it is happening, the location of the movement. So many other fields also there. So one is popular, one is research. So earthquake, when an earthquake comes, people are thinking that it's going to bring some vibration. That is half true. That is, it is not going to bring only the vibration. Sometimes earthquakes will bring liquefaction. Liquefaction is quicksand condition that you must be heard about. Another thing is landslides, volcanic eruptions, so many other extra things also it can bring, which is more dangerous as like our earth. So earthquakes will be responsible for liquefaction or sometimes landslides. So there are different types of magnitudes. As I told, magnitude is the quantitative term, which is related with the seismic energy release. So many other types of scales also followed in magnitude. The most used or the present used one is NW, moment magnitude. This moment magnitude is the universal scale now people are adopting. That's what followed in India. Okay, so this is one important law, power law. Whenever you are start studying about seismology, the basic thing is talking about the power law. So I don't want you to remember the formula, but I can just explain what it says. For example, whenever more number of events are happening, that is called as more number of events are called as, then I can call that as more frequency, or that particular area is having more frequent events. When it comes to less number of events, I can call that area as rare area. So this is the relationship. This power law is going to relate this number of events with magnitude. So this is basically telling us that there is more number of events, usually the magnitude will be very less. Where more number of events are there, very less number of events are there, then you can expect more magnitude. Okay, you can see here, great earthquakes are magnitude more than 8. In a particular year, you can expect only 1. Or if it is a moderate event, maybe 5 to 5.992, it is thousands. Very minor events, 2 to 2.5, that is around lakhs. So that's what they want to explain to the power law. Less number of events, magnitude will be maybe more high. More events, magnitude will be less. That's not useful. Okay, that's what explained in graph. So this is also another important topic, recording of ethics. So can someone ask you think what's the need for recording the events? So people are investing so much of money in this one for recording the events. And not only in India, world level there are so many seismological centers are there. People are investing more instruments, seismographs and other things. Each and every second in the world where and all earthquakes are happening, that is recorded, and people are investing more and more in this particular thing. The reason behind this one is not only to read about our internal pocket. That is one reason to get some idea about the internal portion of your earth. For example, we want to know the soil structure, or you want to know what kind of minerals are available, or what kind of materials they are underneath your crust. You can do some borehole tests, or you can dig up to some meters, that kilometers maximum. But after that, if you want to know what is the property of that particular soil or something, there this seismic wave recordings are going to help you so that each of the layers of the earth also will get some properties. That is one reason. Another one reason which is not to some people, by this base you can get nuclear neighbor countries to any other test, nuclear test, or some other weapon test if they are doing, you can get to record from here without knowing them. So that is also another reason why people are investing money in recording ethics. That's what they call as verification statement. So next, since we know some basic things about ethics, so here I'll just stop for 1 second because we are moving on to the main subject. I just told you till now why ethics is important. First thing is our structures are having the same frequency same frequency of seismic waves. So there is a possibility of resonance. One, then more and more urbanization and population growth is insisting us to study this particular subject. So that's the need for the subject. Next, what are the things we have covered? What is earthquake? How it is happening? What is the property of the seismic waves? That also we have seen. In addition to that one, what are the things we have seen?
what is the magnitude, what is the intensity, how these things are related. So why one has to record the event from the recorded events, what are the benefits are there, what are the magnitude scales are there, which one we are using. All these things are basics about it. Once you are clear about the terminologies what we use and how these rules are probability, what is that, then now we are moving on to earthquake resistant design. So, okay, this is about testing. So, how to safeguard my structure against this kind of phase? So, that was our focus. So, next we will study the earthquake resistant testing. So, this is no way that earthquake is going to hit your structure in its lifetime. This is just a probability. This probability means if you are designing a structure based upon your lifetime of a structure. Lifetime of a structure means if you are designing a residential building, you can consider some 50 years. The resident, if you are designing a hospital building or if you are doing an important building, it may be 50 years. It may be 500 years. Or if you are doing some nuclear reactor, it may be 5,000. So based upon its lifetime, one has to consider what may be the possible earthquake may happen to that particular structure, and I am going to design a structure to safeguard against that particular magnitude. That is earthquake resistant design. So, how to design my structure against it? First thing is I'm going to consider two things here. One is seismic hazard, vulnerability. Seismic hazard. So seismic risk is nothing but the combination of or the multiplication of seismic hazard with vulnerability. That means whenever one earthquake is going to happen to that particular area, first thing is, so how much possibilities is there and to have earthquake to happen in that particular area? So what may be the magnitude? What kind of soil structure is there? Those things will come under this seismic hazard. Vulnerability is nothing but how vulnerable my structure is towards that event. That is vulnerability. So if you see both the terms, this seismic hazard is not in my hand because this is based upon the property of that location. That is based upon the property of the soil. But whereas this vulnerability is in my hand. My hand in a sense as a designer, as a student, I can change the vulnerability of the structure. I can make it more stronger, I can make it more safer. That's why instead of reducing the seismic hazard, I'm going to decrease the vulnerability of my structure and going to play with stability, safety, and strength of my structure. So here, basic design principle is whenever I'm moderate to low magnitude event comes, my structure should withstand that one. Second one, if it is a heavy event, that means a severe magnitude event is going to happen, at least my building should not get collapsed. Okay, that is my focus. So two things. So what is the design principle means? You have to say two different things. One is low magnitude event or a moderate event. The structure should withstand that one with very minor repair works. Okay, when it comes to a large event or a severe event, in that case, building should not get collapsed. It has to give time for my occupants to escape from the building. So this is my focus whenever I start designing my earthquake resistant system. So to start our earthquake resistant system, we need to know about the seismic zone. I hope people would have known about what is seismic zone. Seismic zone is nothing but in our ISO, our whole Indian terrain is divided into 4 different zones based upon the severity of the seismic point. So if we are located in this particular point of India, then you can refer the ISO and find out this particular region is belongs to zone 1, 2, 3, 2, 3, 4, and 5. 1 is removed from the code. So totally 4 zones. Zone 2 is the starting, zone 3, zone 4, and zone 5. Totally 5 zones are there. So in this only 4 zones are. In this 4 zones, if you are lying in the second zone, that means you are in the safest. Okay. That means there is the possibility of event which is coming very rarely. If it comes also, the magnitude can be expected very less. If you are in the zone 5, on contrary to this one, there is the possibility of more number of events. The frequency is so high that it can able to come very soon. But too, the magnitude is the possible magnitude is very high. So this is how they have divided the India into 4 zones: zone 2, 3, 4, and 5. So with this zones only, we are going to start our discussion. So the very long history is there for this seismic zone mapping. This mapping started in our 1950s and that has changed the time to time based on so many things. Okay, first they have started with the prehistoric seismic data and they have considered soil types. They have included some fault data. Then they have changed like this. So this is the figure. So in 1962, India is having 7 zones. Zone 0, 1, 2, 3, 4, up to 6. In 1966, it is changed from one portion of the India to the some other portion of India. That they have changed and delimited that India into different zones. Then 1975 is in zone 2. 1975 is changed. 1984 again one more version. Presently, we are following this 4-zone map. So when this one particular revision to another particular region, we are just putting more and more inputs about fault tectonics, then past seismology data, soil properties, and whenever an event happens, what is the intensity mass around that particular epicenter. These things are taken as a reference and they have changed the soil properties, how their amplification is going to happen, size amplification is happening in this particular area. Those things they consider and they have come up with this. So now you can see this last but one, 7th one as a practice. Now, if you are start defining today, you have to follow this one. That's the 8th map, which I have shown in the last, nothing much. The 2024 revision of our code. Here, people have proposed a 5-zone mapping, which is having 2, 3, 4, 5 as well. 6th zone also. This is not yet come to practice. It is in draft stage. In 2025, around March or February, you can expect this particular code to come to practice. So if you start designing, you have to use the figure number 7, or if you start designing a structure maybe in the next year, you have to do this particular one. Since it is in the draft, but still you can see it has changed the main portions in India, whereas the zone 2 and all moved to 3, 3 has moved to 4, and so many changes they have brought. They consider so new inputs like returns, and they have assigned some new events to new faults and other things like that. Lineaments, patterns, everything they have considered. So we wait for this particular revision to come to practice. Here then we will follow the 7th. Okay, so this is the one we are following. So this, in addition to this map, we have one annexure also in the code. In that, people are given for important cities. For example, you are in Hyderabad, or you are near to Rampur, or you are near to Rampur. You can see they have given the particular seismic zone numbers for the cities. You can see Delhi also they have pointed out. Varanasi is there, Patna is there, Hyderabad is there, Bangalore is there, Chennai is there. So whenever you are designing the building in an important city, you can directly take the value from the annexure instead of referring this particular zone. If the zone may be in between one zone to another zone, and other things may be confusing at that stage. So they brought an annexure where you can clearly take the seismic zone map value from the annexure. Okay, so now we will see how to define our structures from the planning level. So once the planning level, you are confident that it is going to resist the seismic waves. So when you are moving to detail, okay, planning, designing, and detailing. So planning stage, we will start our seismic resistance properties. Then we will move on to design thought. Then finally, we'll see how to do the detailing to safeguard against the seismic risk. Detailing is nothing but ductile detailing. How to incorporate more ductile properties into our structures. That's what finally we are going to see. First, we will see about planning stage. So whenever you are designing a building, concentrate more on building configurations. This configuration is nothing but uh, if you see from the plan or elevation, how it's going to look like, whether it is having a regular pattern or irregular. So those things you can easily do in the planning stage so that your building can easily resist against the second stage. So these things you will see one by one. First one is selection of load resistance system. What is load resistance system? This is nothing but your skeleton of your building. Skeleton is nothing but the combination of beams and parts. So usually our skeleton will be straight. Our lateral load resistance system will be usually same. So if you see whatever may be the type of building, your load resistance system will be lateral load resistance system will be an RC framework. If your RC framework is selected based upon the RC framework, you can see from this one. We are calling that one as moment resisting frame. It may be a moment resisting frame, that means barely it is having the combination of beams and parts. Another type is called as shear wall type. Shear wall type is nothing but a concrete wall which is going to resist your lateral movement of your building. So we can just imagine a lift lobby. So lift lobby is a perfect example for shear wall. So some buildings may be a combination of this water resisting frames, lateral load resisting frames, combination with some shear walls. So that is a perfect system because it is economical as well as it can able to resist more lateral loads. So if you start designing a building, better to go for a dual system. Okay, so then we will move on to the configuration. When it comes to configuration, first shape, size, and arrangement of structural elements and most of the structures are going to play a role to make it regular. Regular and irregular are basic terms. You can easily understand by the words what it means. So regular means this is the building. For example, if you consider a central line of the building, left and right portions should be more arranged right so that it can able to balance the section. If you are going for the irregular buildings, it may be vertical irregularity or horizontal irregularity. It's going to bring some kind of discontinuous in the load part. I hope you can understand what this load part. Load part means the seismic energy is transferred from seismic waves to your foundation. From the foundation, it may be transferred to the next level beams and columns. Then it will move on to the one more floor, till it go to the topmost floor. Once it reaches the topmost floor, it can be able to come back in the foundation and again it will be dissipated in the soil. So if this part is smooth and it is continuous, then you will be having very low impact. If you are following a regular building in plan as well as elevation, this path will be smooth as well as there will not be any gaps. If that is the case, your building can be able to resist more seismic loads. So these are the things we are going to see. Vertical irregularity. Irregularity may be in the form of thickness or strength or mass, whatever may be. Irregularity in these possibilities should be avoided to perform better against seismic loads. Horizontal irregularity is also possible. That is, people may be adapted some kind of different shapes to the building, or they may go for some cutouts. For example, you want to take the heat from one floor to another floor, then you have to cut the flooring, and you have to take it from that one. So there are some codal provisions. How much area in this single slab I can be able to go for. Okay, in addition to that one, I have no other options. I go for setup. I can go for the reinforcement and the model and the rules sometimes. I can able to follow that ones, I can go for larger things or large cutters. Then another term is re-entrance cost. For example, you have two wings, like L-shaped building. If you want to avoid the technique performance, bad performance, then you have to divide that one into two wings, provide a small gap in between, unless otherwise it may put your building into a re-entrance corner effect. That's a possibility that the specific will develop on that particular point. This is an example, this figure is an example for re-entrance point. Okay, so this is what I was talking about the continuity load part. You can say the foundation is moved from yourself to further in the front direction. If your foundation is moved away from you, the first story here walls is going to move towards you. The second floor slab is going to move away from you. When it comes to second story here walls, it will come towards you like this. Which is going to transfer the seismic energy level 1 to level 2, level 2 to 3, 3 to 4, 4 to 5. Again, that 5, 4, 3, 2, 1, 0 is going to travel. If this load path we have ensured without any floating column, without any re-entrance corners, we have provided the smooth path to transfer the seismic load, then there is a possibility that your building going to survive or perform better against the seismic. So these are the things one has to be careful when you are designing that and you are planning the building in the plan stage. If these things are taken care, when it comes to design and detailing stage, it will be more smooth and easy. Okay, so these things are very basic things. That is, now one has to avoid the beams and stuff to do. Definitions are there in the code, but basically what you can consider the bottommost area now people are leaving it for parking and the open stories for some auditorium purpose. These have to be avoided unless otherwise it is really needed because that lowermost floor is the one going to take the flow directly and it is tension in the system. So mass irregularities also when you are designing a building, you should keep taking care that the more mass or the heavier floors should be placed in the bottommost floors. For example, some people are designing the swimming pools at the top or gyms in the topmost floors. It can be avoided and they can gradually reduce the mass of the floors from one floor to another floor in the residence. One more thing nowadays, since we are in the modern city construction, we can't avoid the nearby construction, or we can't provide more gap between the buildings. Still, we have to adjust with the proximity of the new building. That is bounding effect we call because whenever an earthquake event comes, your building starts vibrating in the lateral direction. Your nearby building also starts vibrating in its own natural frequency. If these two are bound against each other, it is going to bring a lot of damage to the topmost floors. So we have to provide a considerable distance between one building to another building by considering the bounding. Okay, so this is what we have discussed about the vertical direction irregularities. These things are planned configuration. When you see from the plan, here also one has to go for a regular building instead of having it planned in some non-parallel systems and other things. So opening should be avoided, re-entrance corners should be avoided. So these things, it still one has to adapt. Then there is some code permission. For example, you can say U by L should be greater than 0.15 to 2 like this, which is K, which is L also provided. So these things of norms from our ISO should be adopted in case one has to go for the re-entrance. Once plan wise and this one is so confident that the plan is perfectly drawn to take care about the performance in plan. Then we have to think about other characteristics which are we call it as going to be the influencing factors in the seismic performance. These are the 9 important things. One is move shapes of the fundamental theories. Okay, what is node state? It's nothing but when you start oscillating your building or vibrating your building, you can see that it may oscillate using different profiles. So we will call that as first few modes are important for vibration. It's we can call it more than 90% of the energy storing first few modes, maybe mode 1 to 3. Correct. So these things we should be known so that we can avoid some kind of nodes in between your flows. Then frequency and ground period. This already we have discussed. Each building is having its own natural frequency, and as well as our soil is also having
Could you please mute all the participants? Sorry, ma'am.
Sir, shall we proceed?
Sorry, madam. Continue, madam.
Okay, I think time is fine. We will move on fast. Okay, next thing is frequency and ground period. As we discussed, the buildings are having natural frequency, and our soil is also having its own frequency. So whenever you are doing the soil test, you have to make sure that in this kind of soil it is going to lie on, and we have to think about the resonance from soil to building mass. The damping property and ductility property is nothing but your building properties, the damping of your structure and ductility of your structural materials. The seismic weight is nothing but your total weight of your building. Redundancy is going to tell you how determined your structure is. Non-structural elements is going to cover about your building doors, windows, and other things because these are the first dimension portions of your building. Then what kind of soil you are going to lie on your building, that means what kind of foundation you are going to adopt, whether it's a pile foundation or rack foundation, whether that's going to suit your building. So whether it is going to have any reputation in that particular soil, in this case, these things one has to study before moving on to design. So earlier we were thinking about the plan, how you are going to do the planning of your building. Next we have seen that what are the other things, the material properties, or the cultural construction, these things are the next one. Next we will move on to design. For design, for each country we have different codes. For our country, we have this IS 1893-2016 version. This is the one code we are going to reload this entire code that is going to give you a lot of information for any beginner to start designing the building. That is one more code is also important. IS 13920. This is the ductile detailing code. This is going to ensure although you are going to design your structure properly, this ductile property of the building is going to ensure that even in terms of earthquake also, your building can sustain little bit long. That is the second thing. So if you want to start designing, you download one of these two codes, it is going to help. Okay, so here we are going to have two different methods. One is technical method. That is a basic method one can use to find this seismic forces. Another one is nodal analysis. So here already I have told you about the objective of earthquake resistant design. First objective is to, if your building is going to check or if it's going to be against a low magnitude event, then it has to sustain without any damage. If it is going to have a large event, at least collapse of the building should be avoided. This is our target. So here one has to consider MCE, that means within the 500 years of my lifetime, if it is happening only 2%, that is it. In 250 years of return period, 10% possibility is okay. These things you don't want to remember. This is already taken care in your code book. In your code book, you can expect these kind of figures that is going to tell you that what is minor shaking, what is moderate shaking, what is strong shaking. In minor shaking, structural things should not be disturbed. Only non-structural things may get disturbed or damaged. When it comes to strong shaking, non-structural things damage, a little bit of damage to the building also fine, but it should not undergo any collapse. So that's the basic philosophy of our earthquake resistant design. That's how our IS 1893 is designed. Okay. So the response spectrum, how this response spectrum arrives, maybe one has to know these basics that I will explain. So whenever an earthquake comes, okay, we are not going to worry about seismic waves and other stuff. Our target is how my building is going to respond to that particular wave. How it is going to respond? It is going to respond in the point of or in the place of displacement or acceleration. So whenever people are reading some response spectrum, how it is arrived is your building or your structure is considered as a single degree of freedom system. For that, you are going to give one input, that is the seismic wave input, and you are going to read its output. Output is nothing but a response. This response may be displacement, it may be velocity, or it may be acceleration. The response is studied and they put it in an expansion. Okay, you are going to see the input as seismic wave, getting the response and record. Getting the response record. So you are going to have a set of responses against each time second. That is the response pattern. So that response pattern you have seen this kind of here in a code book. So this is the one standard response pattern we are using in code. This is having 3 different lines based upon your soil property. Your building may be a hard soil, maybe lying on a hard soil, or medium soil, or soft soil. So based upon that one, you can select any color of that one you want. From that one, you can take the values. So this SA by J is nothing but acceleration of your building. This acceleration is nothing but the response of your building against your seismic wave. Okay, so this is how our method is starting. First method, as I said, very easy method, seismic wave. Second one is response spectrum method, a little bit complicated, but this first we will cover the seismic wave. So this is the formula. dB is nothing but base shear, KH multiplied by W. This formula and the terminology you can get it from the code book. From here, how we are going to deal with the results, that alone we can discuss because of time. So we can see that this Q is nothing but lateral force. So whenever an earthquake comes, my motto, my objective is how much force it may come to my particular force so that I can design my structure against that particular load. I don't want to over-invest here by giving the same value throughout the flows up. Because as I know, when it comes to the seismic waves, the topmost floor is going to have some lesser value, the bottommost floor is going to have more value. So what I'm going to do is, I'm going to find out this one story-wise. Based upon that one, I will start designing my columns because I don't want to try the same start section throughout the height of my building. I can reduce when it's going to the top to next floors. So once that's my models, I'm going to find the base here or lateral force for each floor. For that one, this is the formula. So one can easily work out from the weight of the building. This WI is nothing but the seismic weight. Seismic weight here is dead load of the structure plus live load of the structure and all its components, core concepts, everything you can work out for each floor. You can multiply with the height of the building, you will get the QI. QI is going to tell how much is the design lateral force for each floor. So this is the demand for you to design. Once you know the demand, you can easily give the reinforcement and cross section based upon this. This is the first one. So that is seismic earthquake. Next one is we are going to deal with the dynamic method. So that method is comparatively somewhat serious than the first. So these are the types of analysis. Maybe and move on to the method. So this is the method. Here only difference between our first method and the second method. Here we are going to consider some mode shapes. Mode shapes already I have discussed. Mode shape is nothing but if you are building it start vibration, the first move that is going to get adapted. After some time it will be fixed in the second mode, then third mode, like this it will progress throughout its vibration. So first 2 moves only we are going to consider because first 2-3 moves are going to contribute more than 90% of your energy. So maybe first 1, 2, 3 one can adapt. So you can see in this one, in the first story, there is no juice. In the second story, you can see that one time it has crossed left to right. So there is a zero. That we call it as node. So here the time history method is another option. Time history takes nothing but cyclic days which are getting recorded. So already we have seen what's the need of recording, how people are recording in these days. So those recording aspects will be given as an input to this building and we will study its response. For example, if that building is going to survive that particular event time state, and it means the acceleration profile, then we can able to say that future also it can able to survive this kind of waves. Okay, so this is the code which we are using for dynamic analysis, modal or modal analysis. This MK is nothing but modal mass. Here, how much each floor is going to contribute to the total. It works out like this. This is node participation factor. So these things are taken from the IS 1892 photo. Here there are step-by-step things are given. That of the time we will just move on after step. So finally, you are going to find out from roof to bottom what is the value of Q1, Q2, Q3 using this one. Only difference between our physical method and this method is here we are going to contribute or we are going to concentrate on nodal participation factors. First few important modes or sometimes we will consider all the modes also for important values and we will check how much is the force. So this here force is going to get affected or it is going to be imposed in that particular place and we can define the building against that. So this damping ratios and other things as per our code book, we are going to use only R perspective. For that we can blindly take 5% damping ratio. Next thing, this is what I told you. Although you can able to concentrate more on the plant configuration and different codes, this is an important topic that is called ductile detailing. Ductile detailing, one of the use IS 13920 2016 version. You can see that whenever a building is going to have only the structural design and the structural plan configuration and other things, you can perform better, but still for the same amount, you can design the same building with ductile detailing where you can cut down lots of extra money. It's going to follow steel and other materials. You can have more ductile properties. You can reduce lot of amount. Okay, because this ductility is going to perform an important point when you are having seismic exposure. So this figure you can see that we always go for strong column beam design because if the story is collapsed, it will not going to lead any progressive collapse. We are going for the other way. One story collapse is going to progress in such a way that it may collapse to the whole building. So why it is not important? It is not going to fail in case of model C. And more thing is, as I told, it is very economical to design your structure. So better to use the trees which are having more ductility. Medium area steel and these things we have taken from code only. So for example, what is ductile detailing? One can see this one. We can see about any joint. Joint means beam column joint. Here, ordinary column, you will be just taking your beams reinforcement to the column reinforcement into the beam, but there is no provision. So when you want to ensure the activity of beam column joint, there is a rule that one has to bend this one in this particular angle, and this has to be taken inside your column up to LB plus 10 times of the. Okay, then in the other direction also, LB is nothing but development length. DB is nothing but ball diameter is not rectangular. So if you follow this one, this particular joint is ductile joint where it can able to ductile or it can able to elongate further in case of event, and it is going to bring some extra performance in case of event. So like this, each and everything for defining a column, for defining a beam or beam column joint or shear wall, we have separate ductile points. So what may be the minimum spacing, what may be the minimum diameter, how much I have to extend inside the column. So I want to go for splicing. Splicing is nothing but if you want to have one more reinforcement, if it's flat over, I want to go for extending one more. How to join these that like this. For each thing, I have some set of provisions. Those if you follow, that is going to provide some extra life to your building within economical range. So this is the being column join details. So check your code book and refer. So this is shear wall. So shear wall design, actually a slicer shear wall design will be having two curtains in the front and back. It's having some end portions for the shear wall design also. That you can refer code book. Time being, we can move on to the application. Okay. So when it comes to application, you are following the good planning, till you are doing the designing, then you are going for design. Still, your building has to be safe because it's an important building. You can play with some other new instruments called the dampers or isolators or batings. So these are the small things one can buy and install, or you can do some extra constructions so that it can perform better in construction. Dampers, there are number of types of dampers are available. You can see the pictures. One can buy this in industry and you can install in the building. That is also an extra thing one can adapt to extend the life of a building in case of earthquake. That is with respect to dampers. Types you can see and figures of it and like that. One more thing is base isolation. So base isolation is having some few disadvantages, that is it cannot be taken or it cannot be installed for the high story buildings. For example, skyscrapers one can go for base isolation because of the frequency. But if it is a medium story building, one can go for base isolation. Base isolators also one can buy from the industry and install. You can see the type of the thing. So this is also another method to protect your system from seismic. If you are designing your building in high seismic areas, in addition to the ductile detailing, in addition to the good designing and planning, one can adopt this kind of isolators or dampers so that your buildings will be having a good life. So I think with this I can stop. I'll open the floor for the questions. If you want to ask some questions, you can ask.
Hello.
My article, you want to ask any questions, you can ask.
Yeah,
Because
madam.
I want to finish by 4:30. I have in the
Yeah,
last minute. If you want to ask some questions, you can ask. I will give my mobile number and as well as my email ID also. If you want to ask some questions, personally, you can ask.
Yeah, ma'am. Thank you very much, ma'am. I welcome I welcome all the participants for this question and answer session. If you have any questions, please unmute yourself and ask the questions. Professor Kavitha will be there to answer your queries. Or else you can post your questions in the chat box. I will read and
I think one person has raised a hand, but this maybe asking questions.
yeah, ma'am. There is no question in the chat box, but we received so many appreciations in chat box. Really, personally, also I
What
also.
I will do is I'll give my mail ID,
Madam.
mobile number also. Maybe some people may be hesitating to ask in front of others. If
Yeah,
they
ma'am.
want to ask something, they can ask through mail also. I will reply them.
Yeah, it will be a great thing, ma'am. Thank you. Thank you very much, ma'am. Ma'am, there is a question from Suket Russia.
Yes.
Where can we find a complete design guide for load-bearing wall when considering seismic design?
Okay. Here, our IS 1893 is suggesting some points for load-bearing walls also. It has some answers for that one. You can follow that one. Still, if you can't find one, our ethics from IIT Roorkee, from our senior military parent, it is having some points which you have to enter only for load-bearing. That also you can do.
There is another question from Nagarajan, ma'am.
Mm.
How can the future design of RC buildings contribute to addressing the global housing crisis and urbanization challenges?
No, I didn't understand.
How can I repeat it, ma'am?
Yes.
How can the future design of RC building contribute to address global housing crisis and urbanization challenges?
Global housing.
Mm.
Ah. No, it is not relevant for ethics. He just wants to ask some basic questions.
There are sir, Professor Nagarajan is asking you to comment on urbanization challenges and global housing crisis in the aspect of RC building.
Let's understand. The thing is, only solution is going for tall buildings
Okay.
because of urbanization and other things, we have to design only tall buildings. So if you want to master in something, instead of new areas you want to explore, better to study the design of tall structures or better to study the design of skyscrapers. So that is your future. How to design normal building is going to be 100% different from your tall building design. If you get mastered in that one, that will be a future of our civil engineering. So tall building design or the design of tall buildings will be the solution for urbanization. That will be the solution for the global housing. Everything. That's what I think. These people are suggesting.
Yeah, thank you. Actually, two persons asked the same question.
Mm-hmm.
Uh, how can we integrate artificial intelligence and machine learning with
Mm-hmm.
RC buildings?
This ask the building.
How
Or
can we
design they want us.
how can we
Design they
integrate?
want.
Yeah.
Mm.
How can we integrate machine learning and artificial intelligence in the design of RC buildings?
Yeah, design. Okay. Actually, what is happening is nowadays we are having so many tools for design. For example, a stat board, SAP or UTAS, everything is going to design a steel buildings or a concrete building. But what one can design, for example, you want to try something in research area, you can write some artificial neural network code which can minimize these things. For example, if you want to design a building, finally it is going to get that design is going to tell that this particular element is not having the capacity of beams and columns. Maybe this if they adopt for 6 mm or 8 mm, it is not having. Then you have to redesign. Then after redesigning, one column may fail. Then you have to redesign. Then finally, one more column may be having failed because of less area. So what you can do is you can just implement an artificial neural network code to optimize this. For example, what people are doing is if I have that the four number of bars of 20 throughout the building, if it is showing safe, then I will just leave and I will adapt it. For example, if I adapt to a neural network code or machine learning code, this one, and it can optimize for each thing. For example, it is sufficient to go for four number of 16 in this particular beam. Next beam may be sufficient 220 and 260. Next maybe requiring 420. So that individual design of each number may be designed with the help of machine learning tools. This will help you to cut down lots of self weight. That area also I'm telling, not only the reinforcement diameter, the area of that particular element also can be cut down, and it will reduce lots of dead weight, and we can be so confident that we have designed the structure which is having very optimum level of design. That one can help. Anything else? Just read some of it.
There is a question from Dr. Pankaj.
Yes.
Dr. Pankaj is asking that, shall you discuss about fundamental frequency of low-rise buildings?
Yeah, the formula, actual formula for finding the natural efficiency is different. Whatever I have shared is, if, for example, you are going to the roadside or to the site and you are seeing a building, nearby building is having some 4 story, 5 story, next building is having 10 story. In between, your building is going to be constructed. At that time, you may not have that sufficient calculator or some properties to work out the natural frequency. Immediately, if you want to find out the frequency of this particular building, the basic formula is 1 by 0.1 times the number of floors. If 3 story building is there, 1 by 0.1 multiplied by 3, 1 by 0.3 is the answer. So that is basic formula, but the actual formula, if you want to work out, you know that activity, you must be knowing that frequency, those things you need. That you have to work out in here, not this basic formula.
Really, ma'am, thank you very much from bottom of my heart. Really, I impressed with your presentation. I am receiving so many appreciations in the chat box. On behalf of organizing committee and the participants, I extend my heartfelt thanks to you, ma'am. Really, you enlightened us with a beautiful presentation on earthquake design and concepts. Once again, thank you for taking the time to be with us and for your invaluable guidance. We hope yeah, we have another privilege of working with you again in the future. Thank you very much, ma'am.
Thank you so much. Thanks for all the questions.
Ma'am, if you don't mind, could you please give your, can I share your mail ID in the chat box? Why? Because I'm receiving so many questions.
Okay, well, yes, sir, I will do.
Okay.
Elizabeth, sir?
In chat box, ma'am.
I am sure, doctor.
Yeah. We got it, ma'am. Really, thank you very much, ma'am. Thank you very much.
I can leave the session.
Yeah, ma'am. Thank you very much, ma'am. Dear participants, yes, we informed from 4:30 to 5, there will be a break. As many of our faculty are leaving the colleges. Once we reached and settled at home, we will come back to you at 5 o'clock with session 12. Thank you, everyone.